Hand someone a $20 bill, and you no longer have it. That's the nature of physical objects. But copy a digital file, a song, a photo, a document, and now you both have it. That's the nature of information. Building money out of something that can be perfectly copied for free, that's the problem that stumped the world's best cryptographers for 2 decades. Every single attempt failed until 2008, when an anonymous stranger posted a 9-page paper and vanished. To understand Bitcoin's breakthrough, first understand what makes digital money so hard. Any form of money must pass 3 tests. First, authenticity. Is this money real or counterfeit? Second, uniqueness. Has this same money already been spent elsewhere? This is called the double spend problem, spending the same legitimate money twice. Third, ownership. Does the person spending this money rightfully own it? Physical cash handles all 3 effortlessly. Special inks and holographic strips prove authenticity. A paper bill can't physically exist in 2 wallets at once, preventing double spending, and whoever holds the bill owns it. Digital information breaks all 3 properties. Any file can be copied perfectly at 0 cost, unlimited times. There's no holographic strip on a digital dollar. There's no physical constraint preventing duplication, and the possession means nothing when data can be cloned. Cryptographers did solve 2 of these 3 problems: digital signatures, mathematical proofs tied to a private key, verify both authenticity and ownership. But signatures alone cannot prevent someone from sending the same digital coin to 2 different recipients simultaneously. Authenticity and ownership solved. Double spending, the hard one, remained wide open. Cryptographers in the 1990s did find an answer to double spending. It worked until it didn't. When strong cryptography became widely available in the late 1980s, researchers rushed to build digital money. Projects like DigiCash, eGold, and later Liberty Reserve all tackled the problem the same way banks do: a central clearinghouse, one company, one server, keeping the master record of who owns what. Every transaction passed through this central authority, which checked the ledger before approving any transfer. If someone tries to spend the same coin twice, the clearinghouse catches the duplicate and rejects it. Double spending eliminated. The cryptography worked, the systems functioned. But centralization created a fatal vulnerability: one company, one server, one legal target. Governments worried about unregulated currencies knew exactly where to aim. DigiCash filed for bankruptcy in 1998 when its parent company collapsed. The U.S. Department of Justice indicted eGold's operators in 2007. Liberty Reserve was seized and shut down in 2013. The pattern repeated every time: build a digital currency, grow a user base, then watch a single lawsuit or a single company failure destroy the entire system overnight. Every user's money gone. This was the centralization trap. A hub-and-spoke architecture where every user connects to one central node means one well-placed attack kills the entire network. The problem was never the cryptography. The cryptography worked. The problem was that someone had to be in charge of the ledger, and whoever was in charge became the target. What the field needed was a way to agree on transaction validity without anyone being in charge. Computer scientists had a name for this challenge, and for decades many believed it was unsolvable. The problem is called the Byzantine Generals Problem. Picture several army generals surrounding an enemy city. They must coordinate a plan, attack together, or retreat together. A split decision, half attacking, half retreating, means catastrophic defeat. They can communicate only by sending messengers between camps. The complication: some generals might be traitors, deliberately sending contradictory messages. One traitor tells General A, "We attack at dawn," while telling General B, "We retreat at midnight." The loyal generals have no reliable way to reach agreement when they can't trust every participant. Now map this directly onto digital money. Replace the generals with computers scattered worldwide. Replace the messengers with internet connections. Replace attack or retreat with, is this transaction valid or fraudulent? Thousands of computers must agree on a single transaction ledger, and any participant might be dishonest. Without a central authority to settle disputes, reaching consensus, agreement among all participants on what's true, seemed impossible. In 2008, someone found a practical solution. A person or group using the name Satoshi Nakamoto published a 9-page paper titled Bitcoin, a peer-to-peer electronic cash system. Nakamoto didn't invent new cryptography. The breakthrough was combining existing tools in a novel architecture, digital signatures already proven for authenticity and ownership, Hashcash-style proof of work, originally designed to prevent email spam, and peer-to-peer networking, the same technology behind file sharing services. None of these components were new. The innovation was the specific way Nakamoto combined them to solve the double spend problem without any central authority. Here's the mechanism. Instead of a clearinghouse, Bitcoin broadcasts transactions to a global network of computers called miners. These miners compete to solve a computational puzzle roughly every 10 minutes, a lottery. The winner proposes the next block of validated transactions. Every other node independently verifies the block. If valid, it's added to a growing chain of previous blocks, and the lost transactions become permanently recorded. This is proof of work. Cheating requires outcomputing the entire network, which is economically prohibitive. Double spending is prevented not by a trusted authority, but by verifiable math and economic incentives. Then something remarkable happened. The Bitcoin network launched in January 2009. A small group of volunteers ran the software on personal computers. The network grew. In April 2011, Nakamoto stopped communicating and disappeared from public life. The system didn't falter. No single person, not even its creator, controlled Bitcoin. The network's total computational power, called its hash rate, grew exponentially year after year. It survived the loss of its founder. It survived a ban on mining by the Chinese government in 2021 and recovered within months. It survived multiple market crashes, regulatory crackdowns, and years of skepticism. The decentralized design held. Bitcoin didn't just create a new currency, it proved that strangers on the internet could agree on a shared truth without any institution mediating between them. That idea, decentralized consensus, has spawned entirely new fields in distributed computing, cryptography, and economics. Before Bitcoin, every digital money system required trust in a central operator. After Bitcoin, the world had proof that trust could be replaced by transparent computation. Bitcoin was recognized as a genuine breakthrough not just in finance, but in computer science itself. The question was never, can we make digital money? It was, can we make digital money that no one controls? That's what Bitcoin answered.